So today I talk about distance sets, which is a problem where there has been a lot of development during the last 40 years or almost 40 years. So the question is that if I have, for example, some general set in the plane, and then I know that it's sufficiently big in terms of Hausdorff dimension, then I want to know how big is the set of distances, which is a subset of the real line. So this is a continuous version of Erdős discrete distance set problem. Erdős considered the question that you have n points in the plane, and then then I think it's expected that there are 1 over n times square root of logarithm n different distances. And this was essentially solved some years ago by Larry Guth and Ned Scutz, who showed that there are essentially this many distances. So it's up to some logarithmic factor, this was solved. But now this is a continuous version. So I have A in Rn, always a Borel set, and I assume always that n is at least 2. Then the distance set is dA, set of all distances, x minus y, norm x and y are in A. And then for the Erdős problem, the extremal case is something like you take an integer lattice, and so from this you get essentially the worst behavior, or the least number of distances. So you can do the same with this continuous problem, but instead you take some square and then you put the little squares, essentially the scaled version of the integer points. And you put very many small squares, but you can get as big Hausdorff dimension as you want. And then you repeat this inside each of these. And when you go on, you increase the number of the squares in the previous squares. And then you can do some calculations. And you can show that there is a set in the plane. You can get also the similar example in Rn. Well, with this construction, you get it in the plane, so that the Hausdorff dimension of A is 1, and the distance set has 0 Lebesgue measure. And because this is expected to be the somehow extremal case, then the conjecture is that if the dimension is bigger than 1, then this measure is positive. And the conjecture in Rn is that if dimension of A is bigger than n over 2, then the one-dimensional Lebesgue measure of the distance set is positive. But this is open in all dimensions. And the first result was proved by Falconer in 1984, I think. So he showed that if you take... Sorry? Excuse me?
Is the conjecture open when n is 2?
It's open. No, it's open. It's open for all n greater than or equal to 2. Falconer proved that if you replace this with n over 2 plus half, then you get this. So if the dimension is bigger than n over 2 plus half, which is n plus 1 over 2, then you get positive Lebesgue measure. And now what I want to do, I want to describe some progress on this at several stages. The problem as such seems, or maybe in your opinion, perhaps quite special and maybe not so interesting, or then you find it interesting, I don't know. But even if you don't find the problem interesting, one of the interesting things with this is that the problem is very easily stated, but it's very difficult to solve. And many different methods have been developed in connection of this, and some of the very new methods have also involved some deep Fourier analytic methods, for example. And I will say something about this now. Well, this result comes from the fact that if I define the distance measure delta mu, it's a measure on the distance set if mu is a measure on the set A. So this meant that mu is positive and finite measure which is support in A. So this is the most natural definition. You can say that you take the Cartesian product of mu with itself and you take a push forward onto the distance map. Or in other words, delta mu of some set B on the line is product measure of the pairs. Product measure of the pairs, so that the distance generated these pairs is in this set B, and B is a subset of R. So this measure lives in the distance set, when mu lives in A. And now how to prove this thing? Well, if I look at some interval, what this measure does to an interval R plus delta, then I can write this as a convolution, or integral of convolution, chi R delta star mu integrated with respect to mu, where chi R delta is the characteristic function of the set in Rn, so that R is less than norm of Z is less than R plus delta. So this is immediate from this definition. And then I can use Plancherel here to write this in terms of Fourier transforms. So this is integral Fourier transform of chi R delta and Fourier transform of mu. And again, from here comes Fourier transform of mu absolute value, so I have Fourier transform of mu squared, and this is integrated with respect to the Lebesgue measure. And this characteristic function of the annulus is a radial function, and there is a formula for the Fourier transform of radial functions in terms of Bessel functions. Bessel functions have several good estimates, and then you can plug it in there and you can do some estimates. And you will find that this is less than or equal to, I don't care about the dependence of R, there is some constant depending on R, essential is delta. So delta, and then what you get is In plus mu inertia of mu. And this you can take finite. So because as yesterday, the dimension of A is bigger than n plus 1 over 2, there is such measure so that this holds. So when I start with such sets, I put there a measure for which this inertia is finite. I have this estimate, but this estimate now means, forgetting about the dependence of R, which is not important, that delta mu is absolutely continuous with bounded density. So clearly you can get from this that it's absolutely continuous. So it's absolutely continuous and it's even a bounded function. And therefore, Lebesgue measure of the distance set is positive since it supports a non-trivial absolutely continuous measure. So that's the proof of Falconer's theorem. Now, for this, to get delta mu bounded, n plus 1 over 2 is the sharp bound. So there is, or maybe I write, there is mu in measuring Rn when n is 2 or 3, then it is true. So I gave the example in R2 about 40 years ago, and then Josewicz and Senger noticed that my proof, which I claimed that it works in all dimensions, doesn't really work. And they gave an argument in R3, and this example is not known in higher dimensions. But the example in the plane is very easy. You take here some set C whose Hausser dimension is, so I should say I so when S is less than 1, when n is 2, so I talk about the case n equals 2. And S inertia is finite, but delta mu is not bounded. And this example is that you take no, not 1, 3 over 2. So this is the borderline I'm discussing, 3 over 2. You take here some S minus 1 dimensional measure on a Cantor set, and then you take this in Cartesian product with intervals, and then you can rather easily estimate that if you take a point here and you look at the distances here, then there is much concentration on some annuli here, and that will then cause delta mu not to be bounded. So it's fairly easy to see that.
So can it be some LP?
Yeah, I will discuss this now. It can be some LP. So it means that with this, exactly this argument, you cannot get this distance set result below 3 over 2. But so now I assume that n equals 2. So, and I probably say something about the higher dimensional results at the end. So, or maybe it's better that I still use general n. So I proved some, again, in I think 87, that if I look at the spherical averages, sigma mu r, which is integral mu hat RV squared dV over the unit sphere. And then I showed that if sigma mu r, so this is just the average of mu hat squared over sphere of radius r. If sigma mu r squared integrated from 0 to infinity r to the n minus 1 dr is finite, then delta mu is in L2. And then if you have good estimates for the sigma mu r, how they decay at infinity, then you can, there are two factors in this square. You can estimate the one factor, and then the rest of the integral gives you one inertia integral. And in this way you will get to the distance set results. So Tom Wolf proved in, I don't remember, somewhere in 90s, that you get optimal estimate for sigma mu r up to some epsilon. So this is less than or equal to r to the power minus s over 2 plus epsilon, arbitrarily small epsilon, but then the implicit constant depends on epsilon. And you only need such estimate for r bigger than or equal to 1 if S inertia of mu is finite. So for this he used, well, there is some kind of Fourier restriction already in this formula, and he used the methods that they had developed in connection of the restriction theory. And when you plug in this estimate here, then you will get that this integral is finite if you have S inertia finite for some S bigger than 4 over 3. So this implies that S bigger than 4 over 3 and IS mu finite implies that this delta mu is in L2 measure. And this gives that if the dimension of A is bigger than 4 over 3, I write it 1 plus 1 over 3, which is the same as 4 over 3, then the distance set has positive Lebesgue measure. So here we had half above the conjectured value, somewhere there. And now we have 1/3 above it. So we are approaching. So now can you use this method to lower this by? Well, no, you cannot, because there is an example, quite recent, by Guth, Josevich, I don't know if she pronounces O or U, that's a Chinese name, and Wang. I think O and Wang are both students of Larry Guth, and Josevich has been in connection with him earlier. That if S is less than 4 over 3, then there is mu such that everything is now in the plane. IS mu is finite, and the distance measure is not in L2. So to get the distance measure into L2, this 403 is optimal. So how to get further? Well, you can still use maybe L2 method, because it is not necessary to get exactly the distance measure into L2. You can maybe get some modification of it L2, and then you can get these things. I still want to emphasize that I use this L2, L infinity, and I don't say that delta mu is in L1, that it's an integrable function, and then it is absolutely continuous, because what you really do, you use some approximations, and then you show that these approximations belong to L2 with constant independent of the approximation, and then you can go to limit. But if you have L1, then all kinds of measures converge to Dirac delta, for example, in L1, with bounded L1 norms. So it's important to get to some LP. But there is no progress. There might be, but I don't know any way that it would be enough to show that the distance measure is in LP for some p bigger than 1, but no such methods have been developed. But what these people did, so there is a theorem of these people. Maybe I didn't check now. I would have it in these papers, but anyway, it is in these notes in the web page. I think it's 2021, but it's quite recent. It could be also 19, which says that if the dimension of A is bigger than 1 plus 1 over 4, which is 5 over 4, then the distance set has positive Lebesgue measure. And this is the best that is known in the plane at the moment. So there is a still gap of 1 over 4 to this conjecture. So what they do, I try to give some ideas. The proof is quite complicated, but it contains many very interesting ideas, and there are various methods which as such are interesting. So I say something on the proof, but just few things. First, we may assume that A is split into two parts, which are a positive distance to each other, and both are S-dimensional. So I'm assuming that dimension of A is bigger than 5 over 4. And because you just go to some subset, dividing it into such two parts. And both support these Frostman measures with growth condition mu I bxr less than or equal to r to the s for every x and r. And I take some s between here in those, so then I can put this measure there. So s is now bigger than 5 over 4. And what I do, what they do, they actually prove more. They prove that pint distance set has positive measure from many points. So the pint distance set is just the distance set from a point. dxa is the set of all distances when x is fixed, and then you consider y in A. So it's kind of projection, because you take x here, and then you, in a way, you project with circles, and these radii give the members in this distance. But these projection methods that are used for linear projections, they don't really use for that. They don't really work for that kind of projections. But then I can also consider pinned distance measure, which of course is mu measure of y, so that distances from whose value for b is mu measure of y, so the distances from x belong to b. And now what they show is that when I have split this set into two parts, then there is x in the second part such that the pinned distance set from this x has positive measure. And of course, this pinned distance set is a subset of the whole distance set, so this is a stronger statement. And then I don't go to that, but they prove also stronger statements that there are many such points always, but it's enough for this original question to find one point. How do they do it? Now I should go back to this example, although it won't be very obvious, but intuitively it is true, and they claim that this method, what they get, is really method to get rid of train tracks. So this example here is something that if I have a line segment, so what is the first situation for those x's for the instance set problem? It is the point where I get much measure and few distances. So if I am here, then I have only few distances. If I am here, then I have more distances. So this kind of situation kind of induces singularities for the distance measure. And that's what they want to get away. And more concretely, this example is something that they take a rectangle, and then they build what they call train tracks. They build some suitably distributed, very narrow rectangle in the orthogonal direction, and then they leave some gap, and they do it again, and so on, and then they repeat and get a Cantor construction by which they get this example. And this kind of situation should be avoided. So now how to start avoiding it? We fix a large number R, but it doesn't appear anywhere in this explanation what I'm going to say. But that's how one anyway begins, because everything on the Fourier side will happen far away, further away than this chosen R0. And then there's first some kind of wave packet decomposition of this measure, which means that on the this is now on the Fourier side, you consider annulus. So you take sequence of radii 2 to the j R0. So this is Rj and this is Rj plus 1. And then this annulus I split into rectangles which point to the center, to the origin. And maybe here is one which I call tau. And this length of the smaller side is square root Rj. So Rj is big, so this is much smaller than Rj. And then I go to so this is on the frequency side, and then I go to the physical side where I have the unit ball, and I can assume that my set is in the unit disk. And then I cover the unit disk with rectangles and so on. And these have side lengths, so this is essentially almost 1 or 2. It's the same, but this has side length, which is some kind of dual to this side length. So and that means that it is r to the minus half. But you actually need it to be a little bit bigger, so there is some small number delta, which is put there so that you get somewhat substantially bigger than r to the minus half. And these rectangles here are called T. So for every j and every tau, I have this family of rectangles. So when this is the direction of tau, this is also the direction of these rectangles. They are in the same direction. And this family I call T, j, tau. And now,
the bigger one is Rj, right? The radius.
Yes, I'm sorry. Bigger one is Rj plus 1. Yeah. So now the wave packets are done so that these members in the wave packets, they are localized in these rectangles and their Fourier transform is localized there. So what I take psi tau. This is a smooth function which somehow approximates the characteristic function of tau. It could be characteristic function of tau if the characteristic function of tau would be smooth, but since it's not smooth, I have to take something else because it's essential that one has fast decay for the Fourier transforms that is used in many places. And then here I take eta t, which is essentially the characteristic function of t. And then how do I localize this? Do this localization? You can define this operation for any function f. It depends on t. So mtf is its Fourier transform should live here. So I take psi tau and I multiply it by this Fourier transform of f. So this is now living essentially in tau. But then I have to make it function itself to live in t. So I take inverse transform and then here eta t. So this is now living essentially on t. And this is, and the Fourier transform of this is eta t. Fourier transform convolved with psi tau f hat. And this thing essentially lives now on tau because I have this delta here. So if I take the Fourier transform, it lives on some orthogonal rectangle here, but but the length of this rectangle is smaller than this side of the tau, so this convolution doesn't really change it. Change its position too much. So, in a way, this is in some unprecise way, this is controlled by the characteristic function of t, and this is controlled in the characteristic function of tau. And then when you do it somehow, probably you get a decomposition of mu. So I don't even explain what this is. You can figure it out if you want. It's not important for this explanation, but it just comes from this beginning situation that you look at first things in the ball of radius R0, and this is the term that corresponds to that. But then the rest is sum over j and tau. So every annulus and all these rectangles here, and then sum over all these which are generated by those dj tau. Mt mu. So this is the decomposition. And now I start defining the part of mu. Well, it's not actually part of mu, but the thing that comes from mu and is good for this problem. So somehow this idea now relates to this, but it is a little vague, and I don't try to make it sound precise. But look, thinking of this example, you somehow can maybe imagine what kind of parts should be removed from mu1. So we really look at this decomposition for mu1, which was the measure living on A1. And the parts that should be removed is that we say that one of those t's, which is there in dj tau, is bad if it has too much measure, too much mu2 measure. Mu2 is bigger than r to the minus half. So I add here r to the minus half plus delta, and then this is somehow the average measure these rectangles have, because there is the length 1 which they span in this direction, and we want it to be bigger than that, so maybe 2 delta or something. So this simply says that those rectangles which have essentially more than the average measure what those have is called bad. And then it is good if not bad. So there are only good and bad people in this business. And then I can define the good part of mu, which will be in L2. Oh, did I? No. Here. Mu2 is a Frostman measure on A2. So I have two parts, and mu1 is in A1 and mu2 is in A2. So I define mu1 good by this decomposition. So the first part, again, it doesn't matter. Then the sum is over all tau, j, and t as above. Or maybe I write it j, tau, and then sum t in t j tau, but d is good. So I only sum over those rectangles which don't have too much measure. And in this way I form this new measure. So now this is a smooth function because I have used here these smooth functions to define it. But it's not even real necessarily, it's a complex function. So if you think about it as a measure, it's a complex measure. But anyway, there are now two propositions. The first proposition is that when I do this operation, mu1g preserves still quite a lot of mu1 in some sense, so that the norm of mu1 good minus mu1, so you can take this to be the variation norm, or if this would be functions, it would be the L1 norm, is, because I cannot really use this bound for anything, I simply say that it is small. So essentially you can make this small to be some absolute constant, 1 over 1000 or something like this. It doesn't depend on anything. So this is one thing. The second proposition says that mu1g is in L2 in the way that mu1g t mu1 good t absolute value squared so I take the L2 norm over R. Sorry, everything is wrong. No, I didn't think. So this is the distance measure, pin distance measure. So this norm is small. And then also here the distance measure. Actually, I better check. Yeah, it is correct. Sorry.
Just a little confusing. So this distance measure, are we getting their functions?
Sorry?
I mean, the norm what we are considering is the total variation norm.
Yeah.
So in the proposition 1,
Yeah.
their total variation.
Yes.
Not the L1, because we don't know.
Well, yeah, I think you could also start approximating so that everything would be functions and then it would be L1 norm. So, but this is small for x in A2 prime, which A2 prime has small measure, so it doesn't have to be for every x in A2 mu2 measure. But for not many. And this is bounded by some constant, finite constant. So then, once we have this, it's easy to finish the proof. I don't write it because it still takes a little time, but it's easy to see that these things imply the theorem. because this tells you when this is sufficiently small, this delta x mu1 is living on this pin distance set. And because this variation measure is small, this says that large part of this also has to live there. And then it could still be singular and live there. But then when you have the L2 estimate, then that tells you that it's actually absolutely continuous and lives. Well, I mean, its restriction to this pin distance, it is absolutely continuous. Yeah, and you will get positive measure from that. So that's a very short argument. But then I don't have really time to go into details. I'll just say a couple of things. So for the proposition 1, one uses Thomas Orponen's radial projection theorem. If you look at radial projections from x, this is y minus x divided by y minus x norm. And then he proved that if there is p bigger than 1, and when s is bigger than 1, as it is here, then if you take the radial projection from x of mu1 and you integrate this to the pth power over the, so this goes to the unit sphere, so you take the LP norm of this unit sphere, and then you integrate with respect to this other measure, then this is bounded. So this is the main thing to prove proposition 1, because what is bad for proposition 1, the bad situation is so here this difference is just this sum over bad squares, and the bad squares has large measure. And then if you have x1 here in A1 and here x2 in A2, and they are in the same T, then this is bad. Because then you somehow create, well, for this purpose it is bad because you cannot use the fast decay. If x2 is somewhere far outside this, then you can use the fast decay properties of the Fourier transform, that the Fourier transform becomes very small when you go out from the support. But when you are in this situation, you can't use this. For all other situations, the fast decay properties are used. And in this situation, you have that if you have many such points and you then you project from these points here, and you have many points here, then the radial projection will be rather small, so you have some large measure projecting into small measure, and that somehow violates this quantitative LP property. So in a few words, that's how it is used. And this proof is rather tricky. It's not terribly long and in the end not so difficult, but it's quite nice. And sorry?
Is there a way to intuitively see why you have to decompose the measure into two parts? And like here you are defining the choosing good tubes depending on how much mu2 is there on.
Yeah.
However, after that you are decomposing the mu1.
Yeah.
Right. So is there sort of a easy way to understand why you
Well, there are various reasons, but you somehow want to keep away this when you when these points come too close to each other, then you have various problems coming. And one is this, that you can't use this result if you don't have this. Well, you can use it, but no, maybe the more reason is proposition 2. Now when mu1 is function, then this delta x mu1 of t is the integral of the Fourier transform over the sphere centered at x radius t. You can easily check this, and then you can write this as the sigma t convolution mu1 g. Sigma t is the length measure, normalized length measure on the circle of radius t. So this is the same thing then. And then there is a formula of Boch and Liu, which says for arbitrary functions or smooth functions, if you wish, that if you take sigma t and convolve with f squared for every x, integrate this with respect to t from 0 to infinity. This could be allowed to be complex, so I put this. So this is the same as integral from 0 to infinity sigma r hat convolved with f x absolute value dt. So he proved this formula, which is kind of surprising because it's not Plancherel formula, since you don't have Fourier transform of f on the other side. You only have Fourier transform of this length measure. But it comes from Plancherel formula, and it uses the rotational symmetry of the circle.
That's also not the Leibniz measure of the R plus.
Sorry?
It's only dt, right? Not t dt.
No, sorry, it is, you are right. T dt and R dt. This is dr. Yeah, that comes there. And this R is important, but this T is not important. And one of the reasons doing this, that one does this splitting, is that then this T is not important, because if X is in A2, and then when I look at this thing, then it is 0 if T is small. So I can here then just assume that T is essentially 1. But here R is allowed to be big, so there I cannot assume anything. So then this is the same as delta x mu1 good of t squared dt. Now it's essentially the same because of this distance those a1 and a2 have. So I can drop t here, and then I integrate with respect to d mu 2x. And then this will be then essentially the same as what I have here. So I got this from Liu's formula, and here I can forget R. So I get to this thing which I should estimate. This was the thing which I should bound because of the proposition 2. That's what we need. And I can write it into this form, and this magic formula, Liu gives me this decay coming from these Fourier transforms. And then comes the most difficult part of the proof, which I don't have time to explain at all. But you estimate this, you estimate first of this, that this is less than or equal to certain power of R, which I don't give because I cannot explain it anyway, what it matters. But this is the most difficult thing to do. And it uses decoupling, the Bourgain-Demeter decoupling. And there is a lot of decompositions and pigeonholing going there. You decompose the circle into many different parts and other places also. But this number you get there is then essentially bounded by the S inertia of mu1, which can be taken to be finite. And then you will get this. So I only say in words, because my time is up, that in higher dimensions, well, the combination changed a little. I think Larry Good is there, not anymore, but Josevich, and Wang is, and then somebody else. They proved this in higher dimensions, a corresponding thing with the bound n/2 plus 4/3. So this is the borderline. But only if n is even. And the reason for that is that they projected to n/2 plus one-dimensional planes. They used suitable orthogonal projections. And then in this n/2 plus one-dimensional plane, they used Orban's projection theorem. And they couldn't do it if n is odd. If n is odd, there is a partial result of Du and Chang, which somehow is worse than this. And they got this simply by, or not simply by improving the correspondence of the false decay formula for the spherical averages, which was earlier proved. There was a weaker result earlier by Erdogan, and then they improved Erdogan's result to get some number. I think the number this case is, if I still write this number, then the number is n/2 plus n/4 plus 1/, if I remember correctly, 8n minus 4. This corresponds to 4/3 in the plane. But then this is the new number 5/4. And these are the best results that are known in all dimensions. Okay, thank you very much. I stop here now. Sorry?
Suppose you have a set in Rn,
Yeah.
and you know that this D of A, you can say something about its Hausdorff dimension. You know something, let's say Hausdorff dimension is positive. What can we say about the Hausdorff dimension of D? Like the other direction of the problem that you.
Or if you know Hausdorff dimension of the distance set, and what can you say? Oh, well, not very much, because if you have a line segment which is one-dimensional, then this has distance set with positive measure, but the set is only one-dimensional. But of course you always have that Hausser dimension of the distance set is at most Hausser dimension of A. Because this thing that if you think about it like projections, so these kind of circular projections, they don't increase Hausser dimension. So you always have this, and this is essentially, I think, the best you can say. You can really say.
Okay, so then thanks the speaker. Now, this wave packet decomposition.
Sorry?
Wave packet decomposition
Yeah.
for